Hello everyone, it's September 17th. I spent some time this morning reading a book, so kind of late. Alright, let's go into it. So, as tradition might have it, today should be a difficult one, or something not easily handled. Oh, the question is very short. Intersection of two arrays. Given two integer arrays, return an array of their intersection. Each element in the result must appear as many times as it shows in both arrays, and you may return the result in any order. So this will return this, 4, 9, okay, 1000, 1000. What if the given array is already sorted? How would you optimize the algorithm? What if num1 size is small compared to num2 size? Which algorithm is better? What if elements of num2 are sorted on disk and the memory is limited, such that you cannot load all the elements into the memory at once? So this already give you hints. So in the sort them, actually I was taking a information retrieval class, and in there's a system after you tokenize a text, right? You tokenize that text, tokenize the texts of a corpus, all the documents, and you can list a listing for all the words. So each word is correspond to a list of document IDs, and you want to find, say, which document contains a certain number of words, and then you just do intersection of those document ID listings, and there is an algorithm there that can do this listing, do this intersection in O(n plus n) time, which I'm pretty sure is how this is going to be. O(n)m, right? O(n plus m. We sort both, and then we just go one by one. And if they're not matching, then we move one of the pointer. If they're matching, we go, right? And then we move both. And if it's already sorted, then we don't have to sort, because now we have to sort first. And if one is smaller compared to the other, that means we will move along. Oh, if one is smaller compared to the other, we might just binary search it. We can binary search it, right? So pick the one that's smaller, and then we get the one that's larger, and then we just iterate through the smaller one. So each smaller one, we binary search on the larger one to see if it exists. So that will be O small n. Let's say n is smaller than m, so O(n) log m. So we don't even have to. That might be, it depends. It might be faster. But what's the other algorithm? So if we go through both, and then we move, we compare. No, it should be it should be O(m), the larger one, right? So we always compare. So we sort both, and we compare the first one, and we compare the first one if then allow us to find the starting point. That's what it can do. Allow us to find the starting point. That means we can skip a lot of the comparison, and then we can shrink. I see. So in binary search, you can specify the starting point and end point, right? So we have a long list and we have a small list, right? So we will search the smallest in the long list. So for each value in the small list, we binary search in the long list, and because they're all sorted, so wherever we find it, that position will be the starting position for the next round of binary search. So that can also cut down the time. If one of them is stored on disk, you cannot load. So that means you cannot do binary search because it's not loaded. Well, in that case, then we have to iterate. There's no other way. We'll iterate every one from the nums2 compared to nums1. If nums2 is smaller, we keep taking more nums2. If nums1 is smaller, we move. Yeah, so that will be. So we can write both. Given that there's only 1000, it is likely that the non-binary search option will be faster. All right, let's give it a shot. This is not a difficult question. So we broke the tradition from last 2 weeks. Okay, so let's code it up. I pressed the wrong key. There we go. So let's sort them first. Yeah, so we're gonna say nums1 dot sort, nums2 dot sort, right? And then it doesn't matter actually. So we're gonna have I, j, right? I, j equal to 0 and 0. M, n equals len nums, right? Len nums 1 and len nums 2. So while I smaller than n and j smaller than n, whoever goes out first, then we end. And of course, the rest is this, right? So here's what we are going to do. I'm going to say if nums1 I is equal to nums2 j, if they're equal, then rest dot append nums1 j, right? And then I plus equal to 1, j plus equal to 1. We move both at the same time. Elif nums1 I is smaller than nums2 j, right? So 1 is smaller than 2, so I plus equal 1, else 1 is larger than j plus equal to 1. And we return rest. Alright, let's check. We have only 2 examples, 1, 2, 2, 1, and 2, 2 shall return to 2. Next one is 4, 9, 5, and 9, 4, 9, 8, 4. That shall return 4, 9. So we have nums1, right, and nums2 is going to be intersect nums1, nums2. List out of range. How? How do we get list out of range? And we got 1 on 1. Oh, nums1 I. I don't say nums1 j. Alright, let's try this. So this is non-binary search, which I think shall be sufficient. Alright, so that's that. 2-pointer solution, similar to merge sort, right? Similar to merge sort. OM plus n. Is it OM plus n? No, that's not OM plus n. That's just the larger of m or n. No, the smaller of m and n. Each time, no, that's actually the mean of m and n, the smaller one. Oh, but then we have to plus log m. M log m. I forgot the sorting part. M log m plus n log n. So yeah, don't forget to sort it. So we have to sort it first. But if you do binary search, you will have to do the sorting as well. And you have to sort both as well. And then you do binary search. Oh, I think this is actually the one. No, binary search is not necessary. Oops. Press the wrong button. Now I have 2 submissions when nothing actually changed. Okay, so this one scored a 44 milliseconds. 86. I'm gonna say this might be a easy question again. I don't know. I submitted twice. It was an accident. Alright, so go back to problems. Yeah, it's an easy question. Wow, we have like overcompensating. We have a lot more easy questions these days. That's what, 350? Yeah, 350. Hash follow up one line. Oh, the second run. Second run is faster. Although I didn't change anything. Alright, let's see. What do these people have to say? Hash set. Oh, we can do hash. Yeah, we can count them. I just realized you can counter them. Yeah, you can do counter. And then so count number 1, go 2, every single one, you check. You check. That's good. And the swap. That's fine. Counter and oh, what is this? Is it oh, so use counter to avoid sorting. Yeah, binary search if this. Which we can do. Yeah, that's always thinking. So this, but I think the overhead of setting up the counter for only 1000 in length is big. Chain times j. I think oh, this is intersection of counter. Chain to create. Why would you need? Oh, because we're doing this. I create this chain is just like flatten it, right? We flatten it. So counter, that's the one. If it's already sorted, then definitely this one. If one is big, the other is small, it also depends. Binary search is fine, but if the other one, if both are sorted, oh, that means that the other one is not sorted, right? That situation, one is long, one is small, then they're not sorted. If they're not sorted, you have to sort them again. If you sort it, then why use? Oh, you still need binary search because you have to go one by one. Yeah, you binary search it. Alright, that will be it. Very straightforward, but I didn't think about the counter though. Counter is a good solution. Counter is a good solution. Yeah, I think I was influenced by the class, so immediately I just two-pointer. All right. They might ask, right? In the interview, I can see they might ask, okay, can we improve it? Because it's n log n log n. Actually, again, it depends. Depends on the size, right? Depends on the size. OM plus n. Now, OM plus n should be faster. Yeah. Anyhow, that will be it for today. See you guys tomorrow. Adios.